Hi everyone, for today's lesson we are going to learn how to find the probabilities of dependent events. Before we get started, I would like you to please go ahead and factor these four expressions. The first expression is x cubed minus 5x squared. The second one is 2x squared plus 7x minus 15. The third one is 27x cubed plus 1. And the fourth one is x cubed minus 5x squared minus 4x plus 20. When you have an answer, I would like you to please go ahead and restart the video, and we will go ahead and see how well you did. All right, let's go ahead and look at example letter A. For example letter A, x cubed and 5x squared both have in common an x squared. So this is a matter of just factoring out a greatest common factor. Our leftovers is x squared minus 5, and that is it. That's all that you show. For letter B, I'm going to split apart the 2x squared into a 2x and an x. And then I'm going to ask myself, what factors of 15, when working with the factors of 2, will give me a 7? So whenever I think of the number 15, I always think of 3 and 5. So I'm going to do a little bit of guess and check. So I'm going to multiply 2 times 3, and I end up with 6. And 1 times 5 is 5. 6 and 5 will either give me an 11 or a 1. So that tells me that I need to come up with a different approach. So now I'm going to try multiplying 2 times 5. 2 times 5 is 10, and 1 times 3 is 3. 10 and 3 will give me a 13 or a 7, and I want a 7. So I think I found my approach. So I'm going to multiply 2 times 5, and I need that to be a positive 5 because I want a positive 10 to be subtracted from 3. So we have 2 times 5, which is going to give us a 10x, and then I'm going to put a minus 3 in the final space, and that'll give me a minus 3x. And 10 minus 3x is 7x, so I found my factorization. Letter C, this is called a sum of cubes. And in a sum of cubes, we factor this by taking the cube root of our first term, and that's going to go into our first parentheses, which is a binomial. So that's going to be cube root of 27x cubed is 3x, and the cube root of a positive 1 is also a plus 1. Then using that binomial, we're going to do square, opposite, product, square. 3x squared is 9x squared. The opposite of a plus is a minus. Product means 3x times 1, which is 3x, and then 1 squared is a positive 1, and that is my factorization. For letter D, whenever you see 4 terms, we immediately put parentheses around the first 2 terms, change any middle minus signs to plus negatives, and then we put parentheses around the last 2 terms. Then we factor out the GCF of each parenthesis. Once again, x cubed and 5x squared both have in common an x squared, with our leftovers being x minus 5. Then I'm going to write a plus, and if you factor it correctly, or if this is factorable, you should end up with an x minus 5 into the other parentheses. So I'm going to ask myself, what times x equals negative 4x? And that's a minus 4. So I'm going to check, is negative 4 times negative 5 positive 20? Why, yes it is. So now I'm going to write a product of my outsiders and my insiders. So my outsiders is x squared minus 4 times my insiders, which is an x minus 5. Now, x squared minus 4 is a dot, a difference of 2 squares. And I'm going to break that down even further into 2 more parentheses, being x plus 2, x minus 2, and an x minus 5. All right, so hopefully you did okay on factoring. If you are struggling with factoring, please make sure that you come and see me so that we can have a conversation about factoring, since it's not going away and will be on every single test for the rest of the semester. So our learning targets for today's lesson is for you to be able to say, I can find the probability of dependent events given a set of circumstances or conditions, given a table and or a tree diagram. I also want you to be able to say, I can find the probability of 3 or more events, and that is dependent probability. So the probability of dependent events, should I say. So what are dependent events? Well, if 2 events, we'll call them A and B, are considered dependent. So let's say that they are dependent events. That happens if the occurrence of one event affects the occurrence of the other. So an example would be where let's say that you have a deck of 52 cards and you select a card. You keep that card instead of replacing it. Now, the probability of selecting a specific type of another type of card depends on what's in your hand, and it also depends on how many total cards you have. So instead of having 52 cards, because you kept one, you now have 51 cards. So whenever you see the language of without replacement, or you see that we do not replace, something to that effect, that automatically tells you that you're working with dependent events. And that means that your numerator and or your denominator will change. So let's go ahead and look at the next part. Now, the probability of B, that B will occur, given that A has already occurred, is called the conditional probability. The conditional probability of B given A. And the conditional probability of B given A can be written as the probability of B with a longer vertical line given A. And that longer vertical line represents the word given. And that only happens, you only are dealing with this type of notation for dependent events. If your events are independent, you would not use this notation. Now, the probability, if A and B are called dependent events, then the probability that both A and B occur is the following. Probability of A and B is equal to the probability of A times the probability of B given that A has already occurred. So you would just be multiplying your two fractions together. Now, we can identify what the probability of B given A is by working backwards with this formula. If we were to divide both sides by the probability of A, then that would mean that the probability of B given A would be alone, since those two would eliminate. Therefore, the probability of B given A is equal to the probability of A and B divided by the probability of A. Now, in order to make that second formula work to our advantage, I'm going to share with you guys a shortcut. The shortcut is that the probability of A and B really means the number of events that occur in A and B. So the number of things that take place with that are where A and B overlap one another, divided by what is already given. And in this case, that's the probability of A. So divided by the number of things that take place in event A. And this will make more sense once we get into those actual problems, and I will refer back to this shortcut language. So let's go ahead and look at example number 5. It says you randomly select 2 cards from a standard deck of 52 cards. What is the probability that the first card is not a heart and the second card is a heart if you replace the first card before selecting the card, and B, you do not replace the card, do not replace the first card? So we're going to let event A be the first card is not a heart, and let event B be the second card is a heart. Now, if you replace the first card before selecting the second card, then that means events A and B are independent events. And we know that whenever we're working with independent events, we simply multiply our fractions together, and we know that we will be working with the same denominator. So if we wanted to find the probability of not having a heart, or not getting a heart, then getting a heart, then that's with replacement. That means that we need to focus on the number that's going to be equal to the probability of not getting a heart times the probability of getting a heart. So, not getting a heart. Well, there are a total of 13 hearts in a deck of cards. So, if we were to take those 13 away, we would be left with 39 other cards. So, there are 39 cards out of the 52 card deck that are not hearts. So, you have a 39 out of 52 chance of selecting something that is not a heart. Now, we replaced that card, so that means when you select your next card, you still have 52 cards in that deck. And this time we want a heart. So there's 13 hearts in the deck. So I would simplify each fraction individually in order to make this an easier problem. So we have 3/4 times 1/4, and that is equal to 3/16. So the probability of ending up with not a heart and then getting a heart is 3 out of 16. Let's look at letter B. For letter B, if you do not replace the first card before selecting the second card, A and B are considered dependent events because of that not replacement language. We're not replacing it, which means that the denominator and or the numerator could be affected. So once again, we're trying to find the probability of not getting a heart and then getting a heart. So that's going to be equal to our new formula up here, which is the probability of getting a heart, and then timesing it by the probability, the first card is not getting a heart, so I need to have a not heart right here. Timesing it by the probability of getting a heart, given that you did not get a heart the first time. So, once again, the probability of not getting a heart is still going to be 39 out of 52, because that's supposed to happen first. Then, you don't replace your card. You keep it. So, instead of having 52 cards, you now have 51. But let's assume that you won. You didn't get a heart, which is exactly what you wanted. That means that there are still 13 hearts left in the deck. And if you did select a heart the first time, we have a completely different thing that we'll be taking care of, and that's going to be later on in the lesson. So now I'm going to simplify each fraction. So we end up with 3/4 times 13 out of 51. And if you were to multiply straight across and then simplify, you're going to end up with 13 out of 68 as your answer. So we always write our answers as simplified fractions. Let's go ahead and flip the page. Next, we're going to be working with a table, and I'm going to show you a strategy in order to use this table to your advantage. It says the table shows the status of 200 registered college students. What is the probability that a randomly selected student is, let's go with female. So we're going to start with letter A being a female, and then I'll go one at a time. So for one strategy that I would recommend is identifying your totals. Let's find the total number of females. Let's find the total number of males, part-time students, full-time students, because that information is going to come in handy. So the number of female students, we simply add going straight across. 80 plus 40 is 120. 60 plus 20 is 80. 80 plus 60, that is 140. 40 plus 20 is 60. So we've identified our totals. And then another total that's very important is the total number of registered students at this, or college students at the school. So what is the probability that you have a female, that a randomly selected student is a female? Well, there's a total number of 120 females out of the 200 registered students. So that's going to be the probability that you are a female, that a randomly selected person is a female, is 120 out of 200. So we're just going to simplify that fraction. The zeros would eliminate. 12 out of 20 can simplify to be 3/5. And that is your answer. Let's go ahead and look at letter B. For letter B, what is the probability that a randomly selected student, if female, is a full-time student? So that means that given that that person is a female, what is the probability that that person is a full-time student? So this is the probability that you are a full-time student given that you are female. So this is where we would use that shortcut I talked about on the first page. So the shortcut goes like this. Instead of working with the fractions of the probabilities, instead work with the numbers. The number of A and B divided by the number of givens. So what that means is that we're going to identify the number of full-time students and female divided by the number of givens, and we are given female. That is a shortcut, and I can go into greater detail next time I see you in class. So full-time student and female. So my full-time student and female, that's a total of 40 students, divided by the number of females, which is 120. So 40 divided by 120 is 1/3. So the chances that a randomly selected student is a full-time student, given that they are female, is 1/3. Next, letter C says, what is the probability that a randomly selected student is a part-time student? So, probability that we randomly select a part-time student means that we need to identify the total number of part-time students, which in this case is 140, and we're going to divide it by the total number of students, which is 200. So I'm going to eliminate the zeros. 14 over 20 simplifies to 7/10. And that is my probability. The probability that a student is part-time is 7/10. Let's look at letter D. What is the probability that a randomly selected student is a male, given that they are a part-time student? So randomly selected person, probability that a randomly selected person is a male, given that they are a part-time student. Once again, we're going to use that shortcut, which means that we're going to identify the number of male and part-time students, and we're going to divide it by what was given. And what was given is part-time students. So the number of male and part-time students is 60. So that's going to be equal to 60 divided by the total number of part-time students, which is 140. Eliminating the 0, 6 out of 14 can be simplified to 3/7. And that is our answer. All right, so we can just extend what we've already done to 3 or more events. So it says the formula for finding the probabilities of dependent events can be extended to 3 or more events. So an example would be like number 6, where it says your teacher passes around a box of pencils with 10 red pencils, 8 pink pencils, and 13 green pencils. If you and the 2 people in your group are the first to randomly select a pencil, what is the probability that all 3 of you select pink pencils? Okay, so the first thing that we want to do is find the total number of pencils in that box. So I'm going to add together 10 plus 8 plus 13. And 10 plus 8 is 18, and 18 plus 13 is 31. So there are a total of 31 pencils in this box. And if you and the 2 people in your group are the first to randomly select a pencil, what is the probability that all 3 of you select pink pencils? So what we want is the probability that you select a pink, and then your neighbor selects a pink, and then your other neighbor selects a pink. So let's start with you. You are the first person with the box. There are a total of 31 pencils in that box, and there are a total of 8 pink pencils. So 8 out of 31 means you got a pink pencil. And we're going to multiply it by the probability that your neighbor, the person in your group, the next person that's supposed to select a pencil, also randomly selects a pink. So let's say you got a pink. You won. That 3 out of 31 chance worked in your favor, and you kept that pink pencil. That means that there are only 30 pencils left in the box, and you kept one of the pinks. You got it. So that means there are only 7 pink pencils left. Now let's assume you got a pink pencil, and one of the people in your group got a pink pencil, and now it's the next person in your group that needs to select. There are only 29 pencils left in the box, and we are saying that that person wants to get a pink pencil. So assuming that you and your neighbor got a pink pencil, the probability that the next person in your group would get a pink pencil would be 6 out of 29. There are only 6 pink pencils left out of the 29 pencils remaining. And we would just multiply all of those fractions together. And when you simplify the fraction, you'll end up with 56 out of 4,495. And that is your answer. For these types of problems, please try not to overthink them. It's very easy to overthink these problems. Please try not to overthink them. Okay, let's go ahead and look at number 7. So it says, using observations made of drivers arriving at a particular high school, a study reports that 69% of adults wear seatbelts while driving. A high school student also in the car wears a seatbelt 66% of the time when the adult wears a seatbelt, and only 26% of the time when the adult does not wear a seatbelt. So whether or not a student wears a seatbelt is dependent on whether or not the adult wears a seatbelt. We want to figure out what is the probability that a randomly selected high school student in this study wears a seatbelt. So what we can do is create a tree diagram where the probabilities are along the branches, and they can help you to solve this problem. So what we know is that whether or not an adult wears a seatbelt has that information alone has influence on whether or not the student wears a seatbelt. So we know that if an adult wears a seatbelt, that's 69% of the time. So how do you figure out when an adult does not wear a seatbelt? Well, that's going to be the opposite. So, or our complement. So I'm going to go 1 minus 0.69, and that's equal to 0.31. So 31% of the time, an adult does not wear a seatbelt. So these two branches need to add up to 1 in order for it to make sense. So now let's go ahead and say that an adult wears a seatbelt. We know that a high school student also in the car wears a seatbelt 66% of the time when the adult wears a seatbelt. So when the adult wears a seatbelt, what percent of the time does the student not wear a seatbelt? Well, we're going to go 1 minus 0.66. And 1 minus 0.66, that's equal to 0.34. So 34% of the time, when an adult wears a seatbelt, a student does not wear a seatbelt. So now the next part. 31% of the time, an adult does not wear a seatbelt. But 26% of the time, the high school student will wear the seatbelt. Which means that if an adult does not wear the seatbelt, we're going to go 1 minus 0.26 to find out the percent or the probability that a student does not wear a seatbelt as well. And that's going to be 0.74. Now notice that 0.66 and 0.34 and 0.26 and 0.74, both of these probabilities add up to 1 as well. So now once again, we're trying to figure out what is the probability that a student in the study wears a seatbelt. Well, they wear a seatbelt at 2 locations. When an adult wears a seatbelt and a student wears a seatbelt, and then when an adult does not wear a seatbelt and the student wears a seatbelt. So what I have broken down for you is the probability of A and C plus the probability of B and C. And I'm getting the A's from the letters that are identifying the event. So the probability of A and C, regardless of anything else that's taking place, we're just going to be multiplying those 2 probabilities together. So we're essentially multiplying along the branch. So I'm going to multiply 0.69 times 0.66. So that is the probability that if an adult wears a seatbelt, then the student wears a seatbelt. Plus the probability that the adult does not wear a seatbelt times the probability that the student does wear a seatbelt. So we're just multiplying our probabilities that are attached to one another. I do not care about the information about a student not wearing a seatbelt. That is not important. So when I put this into my calculator, I'm going to round to the nearest thousandth, and I end up with 0.536. So that we always run around to the nearest thousandth because that is something that is expected if you sign up for AP Statistics. So we're going to round to the nearest thousandth. So that means that 0.536%, 53.6% of the time, a student in the study wore a seatbelt. We have one more example, and then we are finished with this lesson. For example number 8, it says, Find the probabilities of drawing the given cards from a standard deck of 52 cards with replacement and without replacement. So the first question says, what is the probability that you get a face card and then a 7 and then an ace? And this is with replacement. So you have to know that with replacement is independent. So it's independent. So that means that we're replacing that card each time, and each time we're selecting from 52 cards. It's like starting all over again. And we want to figure out what is the probability of getting a face card, and then a 7, and then an ace. So the probability of getting a face card, well, there are a total of 12 face cards out of the 52 cards. So I'm just going to multiply all of my probabilities together, times the probability of getting a 7. Well, there's a total of 4 7s out of the 52 deck of cards. So we still have 52 cards because we replaced it. We're replacing again, so we still have 52 cards, and we want an ace this time. So there's only 4 aces in there. And so I'm going to simplify all of my fractions. So that's going to be 3 over 13 times 1 over 13 times 1 over 13. And when you multiply all of those numbers together, you end up with 3 out of 2,197. And that is the probability that you end up with a face card and then a 7 and then an ace with replacement. So now we have without replacement, and this is where things change. So we want, once again, the probability of getting a face card and then a 7 and then an ace. And this is without replacement. So that means that once again, we still have 12 out of the 52 cards are face cards. But now, I'm not replacing it. I am going to keep my face card. We're assuming that we won here. We're assuming we got what we're looking for. And I'm going to keep my card. That means there's only 51 cards left in the deck. Now, fortunately, a 7 is not a face card. So that means that there are still 4 7s in the deck. But now I'm going to pull out not only a face card, but I got lucky and I pulled out a 7 as well. Cool. So I don't really care because a 7, I want to get an ace next. So an ace is not a face card or a 7, but I want an ace. There are still 4 aces in the deck, but the deck is now lowered by another 1, which that means that we only have 50 cards left. So I'm going to simplify my fractions, and I have 3 out of 13 times 4 out of 51 times 2 out of 25. And when you multiply all of those fractions together and simplify, you're going to end up with 8 out of 5,525. And that is your answer. All right, let's go ahead and look at letter B. Letter B, we want to get a heart, and then a club, and then another club with replacement. So the probability of getting a heart, and then a club, and then another club. So this is with replacement, so that means each time you're going to restart the process, you're going to have 52 cards. Now, a heart, there's a total of 13 hearts out of the 52, out of the deck of 52 cards, and then let's say I get a heart, and I'm going to put it back. That means I still have 52 cards left, and I want to get a club this time. And there's 13 clubs in the deck. So let's say I do get a club, but I put it back. So now I'm going to have, out of the 52 cards, I want to get another club. So that's going to be 13 cards out of the 52. So this is equal to 1/4 times 1/4 times 1/4, and that is equal to 1 out of 64. So you have a 1 out of 64 chance of getting a heart, and then a club, and then another club. So now let's look at without replacement. So that means that I want a heart, and then a club, and then another club. So the numerator and the denominator could change in this case. So let's say I want a heart. That means that there's 13 out of 52 cards that are hearts. I keep my card, so there's only 51 cards left. And I want a club. Well, fortunately, I grabbed a heart the first time, so we still have 13 clubs left in the deck. But let's say I won. I got a club, which is awesome. And I'm going to keep my club, and I'm going to keep my 2 cards that are still in my hand. And there's only 50 cards left. And on top of that, I'm keeping my club, which means that there's only 12 clubs left. So I have to subtract 1 from my numerator because I have already kept one of the clubs and I only have 12 left. So I'm going to simplify each fraction. So I have 1/4 times 13 out of 51 times 6 out of 25. And when you multiply straight across and simplify, you're going to end up with 13 out of 850. And that is your answer. And that is the end of today's lesson. If you have any questions about today's lesson, please feel free to email me. Otherwise, I hope you have a wonderful day.